Thank you for inviting me down here. Right, right. Whoops, oh, something just popped up. By continuing to be in the meeting, I'm consenting to being recorded. Yes, okay.
Yes.
Continue, excellent. Um, Very nice. So, the theme of this talk is about topological defects in liquid crystals. And I am going to try to show you that there's a lot more to topological defects than topology. And so let me try to illustrate all of these aspects. So this is work that I have been doing with my former graduate student, Xingzhou Tang, now a postdoc with Wanda Pablo at University of Chicago, and my current graduate student, Cheng Long at Kent State. All right, so to begin here, I'm going to give you a quick little intro to liquid crystals, both conventional and active, just in case there's anybody on this call who's not so familiar with these materials. And then I'll move on to talk about topological defects, this range of properties, topology, geometry, energy and forces, and dynamics. And I'll go through all of that in 2 dimensions and then extend it to 3 dimensions. All right, so to begin with, for my quick intro, so the term liquid crystals refers to a class of phases which have some partial order. So more order than isotropic liquids, less than full 3-dimensional crystals. So these phases are typically composed of long organic molecules with the structure up here. Do you see the pointer, by the way?
Yeah.
I think, yes, okay. Oh, and I can make it a laser pointer.
There we go.
Cool, okay, great. Typically composed of molecules like this, which we can coarse grain. I don't want to look at the molecular structure, so I'll take a more abstract view and represent this as if it's an arrow, which points in some characteristic direction. Okay, and then in a liquid crystal phase, we of course have many such arrows, like 10 to the 23rd of them. Then we can ask, what is the ordering of the direction of the arrows? And in the most common liquid crystal phase, called the nematic liquid crystal, these arrows tend to align like magnetic order in a ferromagnet, but they're not just pointing in one direction, they're pointing back and forth along some axis. And so that's what's illustrated in this ensemble. And then we can characterize the overall direction of order by this double-headed arrow. So the phase with this type of order goes by the name of the nematic liquid crystal phase. The double-headed arrow is called the nematic director, represented as a unit vector. And then we can also characterize the magnitude of the order, how well these things are aligned, by some scalar order parameter S. And together, the magnitude and direction form a tensor order parameter. It's a rank 2 tensor rather than a vector because of the double direction aspect of the ordering. So a tensor conventionally written as Q sub alpha beta with this combination of magnitude and direction. Now we can zoom out some more and say, if we look at an even wider range, what happens to this double-headed direction over long length and time scales? And it might not be uniform. It might be modulated in some way. And so we could get a variation like this. and then might have topological defects in it, right? This non-uniform order might form defects with structures like these. So that is structures where you have a variation in the director field as a function of position, which goes around through some kind of loop, and then there's a singularity right in the middle. And I'll be talking about these pictures in more detail coming up. Okay. So that's the basic intro to conventional liquid crystals. Now, there's also a class of materials that have been studied more recently, go by the general term of active liquid crystals. The term active liquid crystals refers to systems that are not in thermal equilibrium. They consume energy and convert it to movement. And so this concept was originally developed to describe groups of animals moving together, like flocks of birds or schools of fish. And more recently, it's been applied to really a wide range of systems in biological physics. So swarms of bacteria, growth of epithelial tissue, as well as synthetic materials like self-propelled colloidal particles. So here's an example of active liquid crystals. Okay, so here's an experiment from the lab of Zvonimir Dojic, formerly at Brandeis, now at UCSB. So an experiment on an active material based on microtubules. And you can see a two-dimensional experiment in this movie over here, right? So one thing to notice is that the material is always in motion, right? It doesn't just hold still for us to look at. Another thing to notice is that this material forms a lot of topological defects that keep moving around. So an object like this one by my pointer is a topological defect of charge 1/2, positive 1/2, like the illustrations that I was showing you earlier. Defects like that tend to move a lot. They push forward in some direction, like a motorboat. Okay? And then there are corresponding negative half defects, which look like these triangles. And they don't move so much, but they move around some in response to all the positive defects. So these things are always nucleating and annihilating each other. So they keep moving around. More recently, the same Dojic lab has also done experiments in 3 dimensions. Okay, so here, let me see if I can play this 3-dimensional movie. That's this one over here. So here, they have highlighted the defect cores through extensive data analysis and image processing. They extract the information about the positions of the defect cores and highlight them in green. And so you can see that these systems form a lot of defect loops, and the loops nucleate and annihilate. And so the whole material consists of these loops moving around, coming in and out of existence. So this is the subject that I'm talking about, right? The topological defects that occur in both conventional and active liquid crystals. All right, so these types of topological defects go by the name of disclinations. And in the field of conventional liquid crystals, disclinations have been studied for many years, for decades. But thanks to the growing interest in active liquid crystals, there's been a real renaissance of interest in disclinations. And so the subject is becoming very trendy again. And so there are people working on describing these kinds of topological defects now in both conventional and active liquid crystals. So that's what I want to present to you. And I'm going to start in 2 dimensions and go through the whole story in 2D and then repeat in 3D. Okay, so first for 2 dimensions, all right, here's my picture of sample defect structures in 2D, okay? And so to analyze these kinds of structures, we would want to do a construction sort of akin to Gauss's law, right? So we would want to draw a loop around any defect core, any of the singularities, and see what happens to the orientation of the director as you move around a loop. Okay? So in this example, we can see that the orientation starts off at 0 degrees, and it goes up to 90 and 180 and 270, 360, right? So it goes around by a full 2 pi radians in a positive sense. That is, it rotates around in the counterclockwise sense as we circumnavigate counterclockwise. Okay, and so because of that, we define a topological charge to be 1 over 2 pi times this integral of the change in angle. Okay, so this object that I'm showing you has a topological charge of +1. Okay. Here is the opposite topological charge of -1. Here, as you go around the loop, maybe I can illustrate with my Apple Pencil, right? It goes around in the opposite sense, like this, and comes back around here, so that it goes through the full loop backwards. So the integral of d theta is -2 pi, so this is a topological charge of -1. My illustration, my pencil waving illustration looks fine on my screen, but I think I'm seeing my mirror image, so it probably looks backwards to you guys. I'm sorry about that. I don't think I can figure out how to do it mirror image way. All right, never mind. Here are topological charges of +½ and -½. Okay, here is an example where as you go about this loop, the director rotates through an angle of pi, 180 degrees. This is possible because these things are double-headed arrows, right, representing a distribution function of molecules going in both directions. Okay? So the material can support defects with a half integer topological charge. Okay, so here is a +½ here is the corresponding -½ Okay. So this is topology that has been known for many decades. And so we can see the list of topological charges. It could be positive or negative half integers or integers. Right? But now let me mention a new consideration. Okay? The topological charge is a scalar quantity. But the objects that we're looking at don't look like scalars. They look like they are some kind of oriented objects that are pointing in some direction. So in these illustrations, right, we could see, for example, let's look at this picture in the corner. Here is a +½ disclination. And you can see it has a shape kind of like a comet, right? With a head over here and a tail sticking out in that direction. So it has some kind of vector orientation, which is not captured by the topological charge, which is a scalar. This has always been true, but it became especially obvious with dealing with active liquid crystals because these defects tend to move. They have a characteristic direction of motion, which is either forwards or backwards along the red arrow, depending on the type of material, whether it's extensile or contractile. And so people started to notice this orientation of the defect. Likewise, for a -half defect, it looks like a triad, right? Pointing in 3 characteristic directions. And that's always been about the first thing that students notice in looking at pictures like this, but it is not captured by saying that there is a scalar topological charge of -1/2. For other kinds of defects, well, there's always some characteristic kind of orientation with different types of symmetry, 4-fold in this case, 2-fold in this case. And really, the only exceptional case is the +1 defects, which really look like isotropic objects, that they do not have a characteristic orientation. These things really are scalars. So this is certainly an aspect of the geometry of these materials. As far as I know, the first person who tried to describe this feature mathematically was Luca Gioni with his student Vromans. In 2016, they came up with a vector formalism to describe defect orientation, which works great for a +1/2 defect, like this one. Okay, so they define this red vector P as a unit vector indicating where the director is pointing outwards from the defect, from the central singularity. Fantastic, okay? Then they also came up with a vector description of -1/2 defects. Okay, so here's their illustration of a -1/2 defect, and they came up with a way of describing it by this vector P prime. Now, this looked kind of weird to me, and so this is something that I started working on with my student Xingzhou Tang to see how we could come up with a different thing that would more naturally describe the triad structure. So what we were doing, okay, is, well, beginning with repeating the Jomi construction. Suppose we have a defect of topological charge K in a nomadic director field. Right? So we could characterize that by an angle theta for which way the director is pointing as a function of the angle phi in polar coordinates relative to the singularity at the origin. With a coefficient K, that is the topological charge, and some additive constant theta naught. Okay, and then if we just want to characterize where does the director point, radially outward or inward, we can solve for that. Okay, so that makes a set of outward, radial pointing directions, which are defined modulo this quantity. Okay, so modulo pi over the absolute value of 1 minus k. Okay. So when we come to a +1/2 defect, this thing with a comet-like structure, the angle is defined modulo pi over 1/2, right? So modulo 2 pi. Great, all vector angles are defined modulo 2 pi. So that makes a nice single valued vector. Right? We can determine the that vector from the director field by taking the divergence of this NN tensor. That's just like what Vromans and Giomi did. We can go backwards and determine the director field from the defect orientation vector also. So that works great for a plus half, the thing they did. Right? What about for a minus half? In that case, the angle is defined modulo pi divided by 3/2. Okay, so modulo 120 degrees. Okay, that makes the triad. We see with 3 characteristic orientations sticking outwards. So we could say there's a defect vector, which is a triple valued quantity. But it would be nice to say instead, let's make a rank 3 tensor, which is a single valued quantity to describe this defect orientation.
Jonathan, let me interrupt you for just a second. Robin has a hand up. He seems to be shy about jumping in.
Oh, I didn't even notice. Okay.
So well, characteristically shy. So
Alex, should we just ask direct questions, or
yeah? Oh, you weren't here for that. Yeah, I was saying to Jonathan that I think we're a small enough group that if you have a question, you should jump in.
Okay. So Jonathan, I had a question. Suppose that I have a liquid crystal with a lot of +1 and -1 defects, right? And then one of them doesn't have any orientation associated with it, and the other one does, the +1 and the -1, right? Mm-hmm. In such a system, can you have a kind of supernematic order? Evidently, it doesn't have exactly nematic order because everything is scrambled. But you could imagine that these vectors associated by the +1 defects are all aligned. Is that possible?
It is possible, and apparently something like that actually happens. So in the Dojic lab at Brandeis, back before he moved to UCSB, they seem to find that in active materials when there are a profusion of plus halves and minus halves, that there is this kind of super liquid crystal ordering of the plus half defects, possibly also of the minus half defects, but it's harder to tell. And so this has been a feature of experiments, and there are also simulations that show it as well. So that is a remarkable feature of active liquid crystals. You might wonder, does it require activity? Would it also occur in conventional liquid crystals if you had enough defects, right? I mean, maybe the only reason it's been seen in active liquid crystals is that active liquid crystals have a lot of defects, and conventional liquid crystals don't have so many.
You might imagine that the liquid crystal field mediates an interaction between the direction. I don't know if that is an aligning or not an aligning interaction. Thank you.
Yes, yes. Yeah, I think that's a really interesting feature, which I'm not going to be talking about the ordering specifically in this talk, but I will get into the interaction in just a few minutes.
Thank you.
Great, great. Thanks. And please interrupt with any other questions. That'll be great. Okay, so here is a way of characterizing this triad kind of order, right? And then we could generalize it to any topological defect in a 2D nematic phase and say, yeah, any defect gets a tensor of a certain rank. And this is the appropriate rank for the tensor, 2 times this quantity absolute value of 1 minus k, where k is the topological charge. And so charge 1 is a positive 1 is the special case, because that's where this is a scalar. We can also, so here's a picture of the scalar, right? So the scalar does have an extra degree of freedom, this theta 0 parameter, but in that case, it's not an orientational degree of freedom. It has to do with the properties of the defect, whether the structure is radial or tangential or something in between. We also have a generalization to not just nematic phases, but n-adic phases, right? Phases with n-fold orientational order, and then this 2 gets converted to an n. So n times this absolute value. Okay, so that is geometry, right? That is just descriptive, right? So describing what's happening in the defects. Now, what about more physical properties, like what Robin was asking about a couple minutes ago, of the interaction between defects? There is a classical calculation for the interaction between defects in a 2D nematic phase. Okay. So for the classical calculation, okay, we could say, suppose we have 2 defects with certain positions and certain topological charges. Okay. And then we can calculate the whole director field around these defects everywhere. Okay? We can do that exactly for a material with equal elastic constants. Okay? We can do that exactly. Then we can integrate the elastic free energy over the whole plane. Okay? And then we see, how does this integrated energy depend on the distance between 2 defects? Okay, and then we label that dependence as an interaction between the 2 defects. Okay. It turns out that this interaction depends on the separation logarithmically, right? It looks like the product of the defect charges times the log of the distance between them, which means that the force, the derivative of the potential energy, drops, it's like the product of the charges divided by the distance between them, which is just like Coulomb's law in 2 dimensions, right? So it's a Coulomb-like attraction or repulsion. Like charges repel, unlike charges attract, again, just like Coulomb's law. You know, that's always a satisfying connection to make. But now, if we think of the defects as oriented objects, we might want to say, well, what if we don't just specify the charges and the positions, but we also want to specify the orientations of the 2 defects, right? It seems reasonable that the energy integrated over everything would depend on the relative orientations. Right? So to figure out that dependence, we did a calculation like this. Okay, so here in this picture, suppose you have a -½ defect over here and a +½ defect over there. Right? So in order to specify the orientations, I draw a little circle around each of these defects at some core radius, and I specify the director everywhere on the core. Right? And so I want to calculate what is the director field in all of the light blue region going out to infinity, right? Everywhere except at the core. Right? And so this is a case with one kind of relative orientation. Here's a case with a different relative orientations. Here it's even more different or more different. This calculation can be done exactly through the method of conformal mapping, which is kind of an old-fashioned way of solving Laplace's equation in 2 dimensions. And so based on that, I can get out the exact solution, which is a sum of inverse tangent functions plus this extra piece, okay? So the sum of inverse tangent functions is what you would get if you have the optimal relative orientation, which is like in this picture, right? But if you have some non-optimal relative orientation, then that works. You just have to add on this complicated logarithmic business, right? And so then we can plug that into the Frank free energy, integrate over the whole plane, and we get an interaction free energy, which has these two classical pieces. These things have been known for decades. And then there's this new piece that has to do with the relative orientation of the two defects. So it's something proportional to delta theta squared. Okay, so delta theta is the relative orientation of the two defects minus the optimal relative orientation. Okay, so this creates an orientationally aligning interaction between the two defects. Okay, and so this is basically saying the same thing that Robin speculated about a few minutes ago, right? Of an interaction between defects mediated by the presence of all the liquid crystal director field in between, and it makes an aligning effect between the defects that tends to favor ordering of two. Okay. It is, of course, a further statistical problem to figure out what is the ordering of many. So that then makes a story about the energy of interaction, and the derivative of this makes a story about the force of interaction. Okay. So then we could ask, how does that affect the motion of the defects? Okay. So, you know, there's a classical theory for the dynamics of liquid crystals, Leslie Erickson theory, which goes back again many years, and there are more recent variations that have to do with the Q tensor field instead of the director field. Barris-Edwards theory is the name that goes along with that. These things are used a lot in modeling active liquid crystals now. I have my own ideology about liquid crystal dynamics, which I plan to write up in kind of a book of some sort, okay? But until then, let me just try to pass along my propaganda in a brief way, okay? My propaganda is like this, right? That schematic equations of motion for over-damped materials, like liquid crystals, can be written in this form, that there's some kind of interaction force plus a drag force, plus maybe an active force in active materials, and maybe a constraint force. These are all the forces. They have to add up to zero in an over-damped material. In an under-damped material, that would be mass times acceleration. And in an over-damped material, it's just zero. Right? Then you can express this thing as the derivative of a free energy, right? The interaction force comes from a derivative of the free energy, like on the last slide. These two things, the drag force and the active force, come from a derivative of the Rayleigh dissipation function, right? That you can start by constructing what sort of scalar dissipation function is allowed by symmetry. And then once you construct that, just take derivatives and you get these forces. Incompressibility gives a constraint, okay? That's a constraint that has to go in here through the method of Lagrange multipliers. Right. Then once we do that, we can express the equations of motion by writing all these forces in terms of the director and the flow field, or the order tensor and the flow field. Or we could just say we want to work with macroscopic degrees of freedom, like the defect position and defect orientation. These, a very small number of degrees of freedom that apply to the defects rather than degrees of freedom that apply to the liquid crystals everywhere. Okay, that's my ideology. If you compare it with anybody else's ideology, they will show you, 10 slides of stress tensors, and I show you one nice vector equation. Don't you love my thing? All right. So anyway, I don't want to go into all the math here. I just want to show you some examples of what we get. So here's some movies for examples. Okay. First, here are for conventional liquid crystals. Okay? So on the left here, we have two opposite charge defects, which are attracting each other and annihilating. You can see that if they start off with the optimal orientation, then the interaction force just pulls them straight together. It's a central force. By comparison, if they start off with some non-optimal orientation, then the interaction force is no longer a central force. The interaction force tends to align them, both by making them rotate and by changing their position. And so they move around and kind of get into position, and then they come together. Okay, so this
Jonathan,
makes a sort of S-shaped trajectory. Robin.
Just a question. So on the left-hand side, it's crystal clear. On the right-hand side, for the kind of dynamics you indicate, the picture seems to suggest that you need to rotate molecules far away from the defects. So is this, if your red vector on the right is rotating and you try it on the left, then molecules which are very far from these defects will have to rotate as well, and you might be concerned that that will give very, very slow dynamics. Or do I miss something? Is it that far away they are already canceling because these are opposite topological quantum numbers?
Yes, the thing that you just said, right? That far away, the variations in the field cancel because these are opposite topological quantum numbers. Now, if you have just a single defect that needs to move, right, then, and there's no nearby opposite defect, then you do have to realign molecules that are very far away from the center of the defect. That gives an interesting sort of anomalous drag on the defect, which has been studied by various people over the years, including Leo Radzychowski in the last 10 years or so. And so one feature there is that if you calculate the drag coefficient, the effective drag coefficient on a single defect, okay, with no opposite charged neighbors, that effective drag coefficient diverges logarithmically with the system size.
Okay.
In a system with many defects of opposite charges, then the effective drag would scale as the log of the characteristic separation between.
Because there's some sort of screening effect at long distance.
Yes.
Okay,
yes.
Thank you. Yeah.
Great. So these are examples in conventional liquid crystals. I can show you also some examples in active liquid crystals. Okay, so here is a single plus half defect in an active nematic phase. And you can see it just moves by itself, right? And it moves by itself in the direction of the red arrow because the thing we're simulating is contractile activity. If we were simulating something with extensile activity, it would move just like that in the opposite direction. Yes, we get motion like that. Here is another example where the defect moves and it bumps into a wall like this. And then because it strongly enough wants to move forward, it rotates a little bit and then it slides along the wall. And then when it hits a corner, it turns around and slides back. Okay, so it goes back and forth. Okay, so these are kinds of dynamic behavior that come out of this analysis. And it comes out of this analysis doing simulations. That's what makes the nice movies. It also comes out of the analysis when we just work with 3 or 4 degrees of freedom that has to do with the defect position and orientation. And so those are 2 sort of complementary ways of modeling the same behavior. Okay. So those are some of the kinds of things that you can see in 2D active materials, and these kinds of behavior map onto very extensive experiments in 2D active materials. All right, now that was so much fun in 2 dimensions. Let's do it in 3 dimensions. Oh, wait, Robin, please.
Yeah, can I still ask a question about 2 dimensions?
Yes.
An even simpler system than you would be a 2-dimensional hydrodynamic system where you only have a flow field. So you have only +1 and -1 defects, vortices and that kind. So you might expect to be looking at a 2-dimensional randomly stirred fluid as an active system. And in fact, your PhD advisor, David Nelson, wrote a long paper on randomly stirred fluids. Where he used epsilon expansions and heavy machinery. Could you import that and use it for your active fluid with the same technique for your active pneumatic system? It doesn't use topological defect.
Yeah, that's an interesting thought. I'll have to contemplate that one. That one's not obvious. I mean, the difference between the active liquid crystal system and the active fluid without orientational order is just having this spontaneous orientational order. Right? The fluid by itself has motion. It has vectors associated with it. That's the velocity, but it doesn't have this natural tendency to have a vector with non-zero magnitude. It needs driving to have that.
It doesn't have an interesting static limit, unlike liquid crystals.
Right. That's a great suggestion. I'll ponder that one for a little while.
Thank you.
Great. Okay, 3 dimensions. And so let's see, do I have like, 10 or 15 minutes now? Something like that. Okay, well, I'll try to do this sort of more quickly, but just to highlight the differences between 2D and 3D, because there are some interesting differences between 2D and 3D. Okay, so one aspect of the differences has to do with the topology. And this is not a new thing. This has been known for many years. Okay, you might naively think that any point defect in 2D could be extended to a line defect in 3D, right? That any point like this one could just make a line coming out of your screen, right at you, for this thing or for this thing. Actually, that is not the case. Okay, it is an interesting result of topology that is not the case when the director is free to rotate in 3 dimensions. Okay, and to demonstrate that, I have my little movies. Okay, so in the top movie, what you can see is I was continuously transforming the +½ to a -½ via rotation in the 3rd dimension. So if whoops, can I play that again? Play again, whoops, no, I won't. Oh, and now for the bottom one, I can continuously transform a +1 to no defect at all, to a -1, to no defect at all, and back to a +1, right? I love my movies so much, I'm gonna play them again. Whoops, I think I'm gonna play it again. Previous. Okay, it's +½ Now it's twisted. Now it's minus half. Now it's twisted. Now it's plus half again. Okay. And for this guy, it's plus 1. Now it's no defect. Now it's minus 1. Now it's no defect. Now it's plus 1. So the lesson of that is that these things on the bottom are not defects at all, right? They are topologically equivalent to a non-defect state. So I will cross them off with my laser pointer. And the things on the top, that's just one kind of half-charge defect. In 3D, there's no topological difference between a half-charge defect and a minus half-charge defect. It's the same thing. Okay? So from the point of view of topology, 3D is actually easier than 2D, right? Because in 2D, there are all these different kinds of defects. And in 3D, from the topological point of view, there's only one kind. Okay? But topology isn't everything. Right? In 2D, I told you the story that there are these orientational features that are not captured by topology. Right? What about in 3D? Right? Well, even back in 1969, Friedel and de Gennes recognized that there's some geometric difference between these different kinds of half-charge disclinations, right? That there are some things that look like plus half and some things that look like minus half. Right? So they came up with this rotation vector omega to characterize what's the angle that the director field rotates around. What's the vector that the director field rotates around? Okay, so we can transform this. Whoops, I couldn't pause. We can transform, come on. Go back and forwards again. Back, forwards. As we rotate omega, we can see this range of structures. Right? So when omega, the omega vector is parallel to the tangent vector, then you get something that looks like a plus half defect, and the director is all in the plane. Okay? They call it a plus half wedge disclination. Right? When the omega vector turns around to be perpendicular to the tangent vector, then you get a twisted structure. When the omega vector is anti-parallel to the tangent vector, then you get something that looks like a minus half wedge disclination. Right? So there is this range of structures characterized by the relative angle between tangent vector and the rotation vector omega, which is a geometric aspect of disclination structure that has been known for a long time. Right? But that's not everything. We know it's not everything because we know that the 3D disclination can sometimes look like a plus half or a minus half. And those plus half and minus half already have the orientational features that I told you about in the first part of this talk. And omega doesn't describe those things. Okay? So we need something else. Okay? That needs further geometric information. Okay? So for the extra geometric information, well, part one is I can make a vector. There are various ways to make a vector, and I'll skip over how to do it. But whatever it is, I can make a vector through derivatives of the director or derivatives of the Q-tensor. It's a vector that comes out to be perpendicular to the rotation vector. That corresponds to the defect orientation vector for the plus half. Right? This is something which is biggest for a plus half. It's medium for a twisted disclination. It's 0 for a minus half. So that shows us the vector aspect of the order. Then I can make a third rank tensor, okay, with a combination of director and derivatives of the director or derivatives of the Q-tensor. And then if I decompose this third rank tensor based on how it transforms under rotation about omega, I get a one-fold symmetric component. That's like the vector I already told you about. And a two-fold symmetric component, which shows how the twisted disclination is oriented. And a three-fold symmetric component, which corresponds to the orientation of the minus half. So to make these things more specific, I've got a couple of simulations here, okay? So this is a simulation that shows a conventional liquid crystal cell with a pattern substrate. Right? So it's a pattern substrate that has a plus half in one point on the substrate and a minus half in another point on the substrate. And if you have liquid crystal everywhere in the interior up here, then you get a disclination arch that connects the two surface defects. And the green cylinders show the defect, the director structure around the arch. So I can draw arrows to represent all these features, right? So here's the omega vector. It's pointing upwards everywhere. Here's my p vector. It's big where I have a plus half defect. It's small where I have a minus half. That much is consistent, okay? Here is something to characterize the twisted part of the defect structure. It's big in the middle, and it's zero where the director is planar. And then here's the triad to characterize the minus half part of the structure. It's zero where you have a plus half, and it grows and it becomes biggest over here where it's minus half, and there it identifies the orientation of the triad. And I have the same kind of thing in this example where there are two plus halves connected by a disclination arch, and you get this whole complicated structure where the omega is changing around. It's not uniform everywhere. And then the p vector is biggest when you have plus half structures, and the t triad is biggest where you have the minus half kind of structure in the middle. Okay, so those are my pictures of geometry. Alex, am I out of time?
You are welcome to take a few more minutes if you like. In fact, we might as well. You've set up a good story. Let's see how it goes.
I'll show you briefly something about forces.
Okay.
For any of you who may be familiar with elasticity of crystalline solids, okay, there is a thing called the Peach-Kaler force. Okay, maybe some of you have seen it, some of you haven't. Okay, the point is, crystalline solids are full of defects called dislocations, okay, which are defects in the crystalline order. And if you apply some external stress to a crystal, like you try to shear the crystal, right, that imposed stress field creates a force on the dislocation. That's called the Peach-Kaler force. The equation for it looks like this, okay? The Burgers vector dotted into the stress tensor cross the tangent vector. We can do something similar with disclinations in pneumatic liquid crystals, right? We can say there's something analogous to the Burgers vector. This omega thing is analogous to the Burgers vector. There is something analogous to the stress tensor. That is a situation where you are applying different torques on the top and bottom of a cell. If you take that combination, cross the tangent vector, you get a Peach-Kaler force on the disclination. Okay? Here are some pictures of that. Look, for example, at the picture in this upper right corner. Okay? Here is a picture where I'm rotating the top of the cell one way, and I'm rotating the bottom of the cell in the opposite way. It's like I'm trying to open a jar, right? Opening a jar. And so applying equal and opposite torques. And then if there is a disclination running through the liquid crystal, it experiences a force, which tends to push it in this case, in this rightwards direction. Okay. This is something which was actually worked out by Clayman many years ago, but it's hardly ever been discussed in the liquid crystal literature. I was amazed to sort of rediscover it recently. Okay, so that makes a Peach-Taylor force on disclinations. One reason why that might be important to you, even if you are not twisting liquid crystal cells, is that there is an approach using this method to calculate interactions between different disclinations. The idea there is if we have two disclinations, we can take the stress field from disclination number one and say, well, let's evaluate that stress field at the position for some little segment of disclination number two and see what force it experiences. And then we can integrate along disclination number two to get the total Peach-Taylor force experienced by disclination two. That gives a force which depends on the tangent vectors, T1 and T2, and it also depends on the rotation vectors, omega 1 and omega 2, for these two disclinations. So it is a force which has this kind of complicated dependence on the orientational features. If we take this and apply it to the special case of parallel disclinations, where one looks like a plus half and one looks like a minus half, we get a force that drops off as 1 over r, like a potential energy that depends on the log of r. So this is exactly in agreement with this classical calculation about the interaction energy, but derived through a different method, okay? But now, given that consistency check, we can apply it also to other kinds of problems where you have non-parallel disclinations that are coming close to each other and see if they attract or repel each other. So for something like the Zvonimir-Dojic three-dimensional active liquid crystal experiment, when he sees lots of disclinations moving around and getting close to each other, it gives us a story to interpret. When are these things experiencing attractive forces or repulsive forces? So that is, I think, one nice aspect that we can get out of doing this analysis. Okay, I'm a few minutes over time, and this is maybe a reasonable stopping point. So I will just wrap up with the conclusions here that topological defects are important in conventional liquid crystals. They're especially common in active liquid crystals. And there's more to topological defects than topology. There are all these other aspects of geometry and interactions and dynamics that we want to keep in mind as well. And I will thank my collaborators here, Robin, who many of you know, and former student Xingzhou Tang, current student Cheng Huang. I thank all of them and NSF for support, and thank all of you.
All right, well, let's thank Jonathan. Applause via Zoom is always a little bit off-putting, I understand, but here we are. It's the best we can do. We had a few questions during the talk, but I imagine we have a few minutes for at least one or two more. If not, let me ask you one question. Oh, no, go ahead, Robin.
Since I've been bothering you already a lot with questions. Jonathan, one of your colleagues in Kent State has spent a lot of effort talking about one additional invariant in the Frank energy, which is a total derivative, so it becomes a surface term. Now, I was wondering if that surface term might be important if you are putting an topological defect or more than one topological defect between two walls and rotate that. Does that surface term make any difference?
I have a whole ideology about that surface term, right? The thing that you're just asking about. And I recently wrote an article for Liquid Crystal Reviews, arguing that that whole thing is much simpler than people have thought for a long time. And I thought about presenting an hour-long talk about that for this seminar, and then decided to go with this subject instead. But whenever you're ready, I have an hour-long talk prepared on exactly that subject.
You know that I didn't ask this question, Jonathan.
I'm going to make you regret having asked that question. Yes. But whenever you're ready, I'll give you a private showing of my whole propaganda about that subject. What I could say briefly is that the simple story that I showed you has to do with the system with equal Frank elastic constants.
Yeah.
And the system with equal Frank elastic constants means also that this surface term that you asked about has an equal value. Mm-hmm. And that is included in the concept of equal elastic constants. Okay? And so changing that surface term is like changing the other elastic constants to make them unequal to each other. And yes, it's possible, but it becomes a much more complicated problem, which probably can't be solved exactly, but needs numerical treatment. And so it's a more complicated deal. But it's a subject that I love, and I'll talk about it whenever you let me.
Thank you.
Let's see, any other questions? Well, I did want to ask you one thing, Jonathan. If you, instead of having an active nematic with defects, what if I insert defects with particles with some sort of boundary conditions set into them for the director field to make defects, and I make the defects themselves active? So I could imagine producing, for instance, your plus minus half disclinations defects by inserting colloids with particular surface features. If I spin one of them, if I put an external torque on one of them, according to your calculation, the elastic deformation, the Frank free energy of the liquid crystal, allows me to transmit torques to another one, right?
Yes. And
if that's so, one of these things has this triad of vectors, so it has this threefold symmetry, and one has this single symmetry. Mm-hmm. So do I get like a torque multiplier effect? If I spin one of them once, the other one only turns by a third of the way around the circle. So do I have something like liquid crystal in gears?
That's really interesting. I'll have to ponder that one. That one's not obvious to me.
Yeah. Yeah, because the naive picture is because the triad goes around 3 times.
I think that's right. I think if you turn one by the full 360, that the other one would only turn by 120.
Yeah.
So yes, I think that is right. So that is, of course, for this two-dimensional kind of system, right? So you'd be putting in, two-dimensional colloidal particles, right? And people do put three-dimensional colloidal particles into three-dimensional liquid crystals, and they do induce defects. They often induce very complicated kinds of structures, right? And so they, these particles can induce point-like defects, and the points, excuse me, the particles can induce line defects, and then a line defect could run from one particle over to another particle, where you can get some whole assembly of lines. There's been quite a lot of work, especially from the experimental group of Igor Musevich in Slovenia, about that. But that's a big subject. That's more complicated than what you were asking, but I think that I think you're correct. I'll have to think about that more carefully, but I think you're correct about the 3-to-1 aspect, which maybe could be useful for something. I don't know exactly.
I was just playing with the idea. I don't.
Yeah.
It's not good for anything. I don't really care so much. Although I'm being recorded, so I shouldn't say that. But here we are.
Fair enough.
All right. Well, if there's no other questions, let's thank Jonathan again, and hopefully we'll see you again soon, Jonathan.
May I ask a question?
Oh, of course. I'm sorry, Valentin. Please go ahead.
Yes, so thank you very much for the talk. It was very interesting. I want to ask if you think it is possible to construct a correspondence between this topological charge and spin, because like in quantum field theory, different quantum fields also have different spins, and if they have different spins, they can be described as tensors with different ranks. So it's kind of looks like situations that you have. So like when they have different topological charge, you describe them as tensors with different ranks. So like, do you think that such correspondence is possible?
It sounds reasonable. It sounds like there must be some basic group theoretic justification for that, right? I don't know if I can prove that, but your intuition sounds very reasonable, you know, in general, there is a connection between the rank of a tensor and the symmetry of the sort of thing that it can describe, which is quite simple in 2 dimensions and more complicated in 3 dimensions, right? So in 3 dimensions, people might say, you know, suppose you want to describe something with tetrahedral symmetry, right? What rank tensor would be the lowest order tensor that's not 0 for, you know, that allows for tetrahedral symmetry or any other type of symmetry. And so, yes, I believe there's a very general connection that way.
Thank you.
Great point.
Well, are there any last questions before we say goodnight to Jonathan?
Hi, Alex.
Hi.
This is Shahryar, for those who remember me from old ages. I have a question, something along the same lines. It's not a question, it's just to add something. So in 3D, going from -1 to +1 defects, and from -1 to 0 to +1, I'm sorry, first one was -half to +half, and then -1 to 0 to +half. This like also rings a bell about the spin operator, like lowering operators that go from, if that makes sense. It just reminded me of that.
That I'm not so sure about. Right? So, I mean, there's an interesting way that people visualize the topology, okay? And I didn't put it here in my slides because, you know, I was trying to just like jump to the conclusions without all the math that leads to it, okay? But people visualize the set of all possible orientations as a hemisphere, right? So because there's a double-headed arrow, right? Each point on a hemisphere corresponds to a possible orientation of the director field, right? And then if you go in a loop around the line, you could say that loop maps onto some loop on the hemisphere where any point on the edge is equivalent to the point that's opposite, right? The one point on the equator maps, in Africa, maps onto a point in the equator in the Pacific Ocean, okay? And so then you can say, of all possible loops on the hemisphere, which ones can be shrunk down to nothing and which ones cannot be shrunk down to nothing? Okay. So the loops that correspond to any integer defect, 1 or 2 or -1, any integer, right? Those are loops that can be shrunk down to nothing. And there are some mathematical proofs of that, right? So it's like a loop, on the surface somewhere, make it smaller, 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 it's nothing, okay? But a half integer defect, plus or minus half, right, corresponds to a loop on the hemisphere that goes around from one point on the equator to the opposite point on the equator, and then it teleports back to the first point, right? Because these are equivalent. Right? So a loop like that goes around there and then teleports, right? That cannot be shrunk down to 0. Right? So that says that it's sort of a binary question of, is there a defect or no defect, right? And so the plus half and the minus half or the twisted half, any of those things are just half from the topological point of view. Right? And so it's not a question of raising a plus half to a minus half. There's a whole continuous family of structures that goes between one and the other. Right? And likewise with the 1 and 0 and -1, there's a whole continuous family that takes you from one of those things to another. So there, I think it's a little bit different from quantum mechanical operators that actually, jump somewhere without going through all the things in between.
Thank you very much.
I have a question. I have a couple questions as well. Thanks for the talk. It
Sure.
was good. So during that same part, when you talked about continuously deforming the order parameter direction, isn't the rotation in order parameter space, don't you also have to do a simultaneous rotation in real space in order to maintain the same free energy? Because otherwise, it's not like in magnetization, right? When the rotation of real space is completely decoupled from the rotation of order parameter space. So in those animations, you can't do that without changing the free energy, at least in the three-dimensional case, right?
Excellent point. Yes, you're absolutely right. People working in magnetism would call that spin orbit coupling, right? And that is true in some magnets. Some magnets have a lot of spin orbit coupling, and then that leads to interesting effects. There are people who study skyrmions in magnets who care about that sort of thing a lot. You are correct that in liquid crystals, you need to rotate these two things together in order to get the same free energy. Now, I have two further statements though, okay? One way I can respond to that, I can go on from there, is to say there is a certain approximation in liquid crystal physics, okay? People in liquid crystal physics sometimes leave out that effect, okay? And sometimes use what we call an approximation of equal elastic constants, which basically means neglecting that extra coupling and treating the liquid crystal as if it were a magnet, which has the same energy, say for a 10-degree variation in the director, no matter what the spatial variation is. Right? That's an approximation, which makes calculations far easier. In some experiments, that's approximately true. In other experiments, that's not approximately true. So that's one answer, which has to do with the style of theoretical approach. Okay, a separate answer is the construction that I was doing, where I was rotating the director and not rotating the positions, okay? So those movies that I showed you, those were illustrating a point of topology, okay?
Yeah,
That doesn't have to do with free energy, okay?
yeah.
The topology is, in some sense, an approximation to physics, because in topology, we pretend that any kind of change is either allowed or forbidden, and just yes or no. And we don't say some things cost free energy and other things don't cost free energy. Okay? So from the topological point of view, the kind of changes that I was showing in those Mathematica movies, those are allowed continuous changes. And free energy just doesn't come into the question.
Yeah.
But
Okay.
of course, one of my conclusions here is that there's more to topological defects than topology. And so when you do put in the free energy, you do discover, just as you said, that there are differences in free energy between those things.
Yeah. Okay. I was just double checking because yeah. Right. So
No, you're absolutely right.
Yeah, in 3D, they aren't like distinct, like discrete topological sectors. You can just go and hop from one charge to the other, unlike in the 2D case. But in reality, you have free energy, I think.
In 3D, it costs energy to get from one to another because you're distorting the director field everywhere.
Yeah.
Right? But in 2D, even that's not good enough. You can't get from one to another without actually changing the singularities. Right?
Okay.
And so, which is topologically forbidden. Right? And so in 3D, it's sufficient to mess around with the director field and don't touch the singularities, right? But in 2D, you cannot do that. Right? That's a distinction.
Yeah, that makes sense.
All right.
I had one last comment. Sorry, it's not really a question, but I think that during the part where you were doing the demonstration with the pen, you could still do that on Zoom because I don't think mirroring it changes the charge at all. So I think that.
Oh, that's
Yeah.
That's correct, right? Mirroring changes both the way that my pen moves and also it changes the path. Right. And so it changes both of the things that you were just talking about, right? It changes the trajectory of my pen going around and it changes the orientation of the pen, right? And so those two things still go together, right? But what I was worried about was that my pen was like mapping out what I saw in PowerPoint, right? When I looked at myself on the screen, but that wouldn't work for you, because you don't see the mirror image.
Yeah, okay.
Right, all right.
All right. Thank you, Jonathan. I think at this point, we're keeping you from a well-deserved dinner, especially here on East Coast time. So I think let us just say thank you again and have a great night. And I really appreciate you staying up late to be with us out here on the West Coast.
Hey, thanks again. Let's stay in touch about all these things.
Absolutely. Take care, John.
Okay, very nice. Goodbye.
Goodbye, everybody. I'll turn off the